Deep inside a collapsed industrial tunnel, a drone powers on. Down here, thick dust chokes the air, and a GPS satellite signal is completely non-existent. To survive in this environment, this autonomous machine has to immediately answer two questions. Exactly where is it, and exactly how is it moving? This diagram illustrates a classic robotics dilemma known as the SLAM paradox, Simultaneous Localization and Mapping. A robot needs a map to figure out its location, but it simultaneously requires its exact location to plot that map. To break this loop, the drone cannot rely on outside help. It has to engineer its own spatial awareness entirely from scratch, relying strictly on the sensors bolted to its chassis. Navigating this void requires the robot to convert raw electrical signals from those sensors into a structured internal understanding of the physical space. The first sensory building block is the Inertial Measurement Unit, or IMU. Think of it as the robot's inner ear. It continuously measures raw acceleration and rotational changes at incredibly high frequencies. Through dead reckoning, a robot calculates its position by adding microscopic movements to its last known location. But sensor noise multiplies over time. The calculated trajectory warps away from the true path, causing drift. A machine cannot safely navigate by only feeling its own momentum. Without an external point of reference to anchor itself, it will eventually become lost. That external reference comes from the camera. The drone's eyes provide an objective view of the outside world, but they capture data at a much slower frame rate than the rapid-fire IMU. As the visual feed comes in, the drone's software scans the images to identify features, unique high-contrast pixels, and sharp corners in the environment that stand out from the background. Optical flow tracks these features. By measuring the exact distance and direction specific pixels shift between consecutive frames, the software reverse engineers the physical motion of the camera. Vision provides objective truth, but a camera alone processes reality slowly. Relying solely on visual data, a sudden gust of wind or rapid maneuver causes the drone to crash before the next frame even renders. To solve this, engineers use Visual-Inertial Odometry, or VIO, a mathematical engine designed to fuse these two mismatched sensors together. On this timeline, widely spaced tick marks represent the camera's slow, highly accurate image captures. The empty spaces between them are temporal blind spots. High-frequency IMU data bridges this gap, filling the timeline with densely packed micro-movement measurements. Because the IMU inevitably drifts, the slow visual data acts as a hard reset. Every time a camera frame hits, it mathematically snaps the drifting IMU data back to reality. This continuous cycle of fast prediction and slow correction operates as state estimation, constantly refining the drone's velocity and three-dimensional pose. This fusion provides the high-speed local stability needed for flight, but the system is still operating with total amnesia. It has no memory of where it has been. To move from short-term movement to long-term mapping, the drone takes those 2D optical features and mathematically projects them outward into physical 3D space. This grid builds the drone's memory structure, known as a factor graph. In this space, every location the drone visits becomes a distinct mathematical node, represented by these dots. As the graph grows, every 3D landmark the drone observes is tied to those position nodes by rigid mathematical constraints called edges. The factor graph anchors these points in space, building a permanent geometric record that defines the machine's relationship to the room. Eventually, the drone navigates back into the exact room where it started its flight. Despite the VIO corrections, it carries a small, unavoidable amount of accumulated mapping drift. Then comes a critical millisecond. The software scans the environment and recognizes a unique visual fingerprint that it recorded at the very beginning of the flight. This single act of recognition triggers loop closure. As seen here, the mismatched ends of the trajectories snap together, sending a massive ripple of mathematical correction backward through the entire flight path. This global optimization instantly eliminates the accumulated drift. The factor graph locks into a stabilized 3D map, permanently solving the chicken and egg paradox. We are left with a complete technological trinity. Odometry measures the steps, mapping constructs the environment, and localization anchors the machine inside it. This synthesis of vision and inertia allows machines to translate digital logic into physical navigation, from AR headsets tracking a user's movement to autonomous cars mapping a city street.